All right, our next speaker is Rueda, speaking about geometry of vector values, Lipschitz function.
Okay, thank you for the introduction. Well, first, I want to thank the organizers for the invitation for giving talk today. And I want to thank all of you your attendance because you didn't escape when see the title. Today I want to make a, I don't know if it's strong, but I want to represent the Banach space part of the Congress. And I want to speak about certain geometric property of Banach spaces in the case of vector valued Lipschitz function. I will explain why I want to focus on vector valued Lipschitz functions, but before entering in mathematical content, it's for me a big pleasure to introduce you my collaborator, Johan Langemetz, who sadly couldn't come here. He's from University of Tartu. This collaboration, the one of the top, started when he was doing a one-year stay in Granada, coincided with my very last month of PhD studies. So all the results exposed here, unless the contrary, are in collaboration with him. Okay, let's give the accurate framework of this talk. I want to speak about the space of Lipschitz functions. Let's briefly introduce them. We consider a complete metric space M, and we select a distinguished point. Then, given a Banach space X, we will define Lip0, the space of all the Lipschitz functions from M to X, which vanish at this distinguished point. This is a Banach space when endowed with the classical Lipschitz seminar. Okay. Well, there are some comments to make here. The requirement that all the Lipschitz functions in Lip vanish at a common point forces that the single constant function that this space contains is the zero function. That is why this classical seminar is actually a norm in our space Lip0, and it is indeed a complete norm. Okay. Well, concerning the completeness, there is no loss of generality on assuming it. Essentially because it is well known that every Lipschitz function from a metric space into a complete Banach space can be extended in a unique way and with the same Lipschitz constant to its completion. Okay, so essentially, if you don't have a complete metric space, you complete it, and the resulting Lip0 are isometrically isomorphic. And the latter consideration here is that okay, we have constructed Lip0. And what happens if we construct Lip0 prime with a different distinguished point? What happens is that the mapping that sends f into f minus f of 0 prime is an ontolinear isometry. So the assumption of a distinguished point will be nothing but a technical assumption. Okay, but there is no loss of generality if you needed to select the distinguished point. And finally, I will omit the reference to the Banach space when it is the scalar field R. And we will explain why we will not consider C as canonically. Okay. Well, in the last at least 20 years, many properties of Banach spaces have been analyzed in spaces of Lipschitz functions as well as in their preduals, the Lipschitz free space. I will introduce this Lipschitz free later. Properties like approximation property, the property of being an L1 space in the case of Lipschitz free and an L infinity space in the case of Lip, Octahedrality, the Octahedrality property, etc. However, in many properties, it seems to be a big hole of acknowledgement of what happens if one considers here a vector value Lipschitz function space. This is the case, for instance, of octahedral norms. Okay, and before explaining what happened with octahedrality in Lip0, it makes sense I define octahedral norms. Okay, given a Banach space X, we say that X, or that the norm of X is octahedral if the following condition holds. Given any finite dimensional subspace of X and any epsilon, you can always find an element X acting as a kind of orthogonal vector to the space Y in del one sense. Okay, that is satisfying that the norm of every element of Y plus any scalar number lambda times X is bigger than 1 minus epsilon times the sum of norms for every Y and for every lambda. Well, a bit of history of this topic. This property was introduced in the end of the 80s by Morey and Godfrey, and it attracted the attention of many researchers in these years, like obviously Godfrey and Morey, Robert DeVille, Nigel Calton. And it turns out that this octahedrality characterizes the containment of literal L1. More precisely, a Banach space X contains an isomorphic copy of L1 if and only if admits an equivalent renorming with this property. Okay. And more recently, octahedrality has received attention from geometries of Banach spaces because it has shown a strong connection with the diameter to property work. I will not enter in details. Let me just point out for practical convenience that in the definition of octahedrality, we can replace finite dimensional subspaces with finite subsets. So I will let written here, X is octahedral if and only if given finitely many vectors in the sphere of X, given any epsilon, you can find an element in the sphere which is far away from all of them. Okay. This will be the practical definition that we will use. Reinis is looking at me. This was proved by Reinis, Haller, Langemes, and Mark Polver. Okay. And what is the relation of octahedrality and our little spaces? Well, it was a consequence of a big collective effort. And with a collective, I mean a successive papers of Ivagno, Cades, and Werner, later Garcia Lirola, Prohaska, and myself, Professor Avilés, and Martinez Cervantes, that rise into the following characterization. Given a complete metric space M, it is equivalent that Lipschitz is octahedral. M is what is known length, which means that the distance between any 2 points can be computed as the infimum of the less rectifiable curvature in them. In the case of Banach spaces, you can think that in convex subset of a Banach space is an example of a length metric space. The big point of this characterization is that this is a property of M. This is a property of M which allows you to determine whether or not it will produce an octahedral Lipschitz space, kind of metric characterization of octahedral. This is equivalent to the fact that every Lipschitz function approximates its Lipschitz norm at arbitrarily close points. And even in a more located way, for every f and every epsilon, the set of epsilon points of f is infinite, where a point is said to be infinite if, essentially because since f approximates its Lipschitz norm at every neighborhood of the point x. If you consider for a f and epsilon the set of epsilon points, octahedrality is equivalent to this set being infinite for every epsilon and for every f. And in order to justify the presence of Vladimir Cades and Dirk Werner, this is actually equivalent to the fact that Lip has the Doavet property, which I remind here that this means that every rank 1 operator satisfies the Doavet equation. Okay. Well, here we have a very nice characterization of this octahedrality condition in a Lipschitz. And the point now is what happened in the vector valued case. It would be natural that if you take a length metric space or a space where all the Lipschitz functions approximate the norm at arbitrary cross points, this should produce vector valued Lipschitz function spaces. So if we want to face this problem, there is a natural attempt here. The first natural idea is say, let's try to copy the proof of this theorem. Okay, let's go. For that, well, we will go from 3 into 1. Okay. So we will assume that the Lipschitz functions approximate the norm as arbitrary cross point, and let's prove that Lip is octahedral. What do we have to prove? That given finitely many functions, I can find a simultaneously far away Lipschitz function. Okay. Now, for every I pick xi an epsilon point, a point where fi approximates its Lipschitz norm. I can take them different because I'm assuming that the set of epsilon points is infinite. Okay, and we want to construct a faraway function. With this idea, I will dare to make a drawing. Imagine that we have, let's say, 3 epsilon points. If they are different, I can separate them by these joint bonds. Okay. Now, I know that in every ball center at x1, f1, epsilon approximates its norm. So I'm taking a smaller radius r, little r, and I'm taking here a pair of points where I know that f1 has a big increasing quotient. I do the same here, and I do the same here. And now I want to construct G. How will I construct G? I will do the following. I will take G so that it will have big increasing quotient in all the pairings. Okay, that is in order to make the sum of fi plus G big in norm. Okay, and I'm defining 0 out of the big box. Okay, now see if R is small enough, this Lipschitz function can be proved to have norm less than 1. What I need is to have G defined not only on this subspace but also in the whole F. But there is no problem. There is no problem because Mac-Chain extension theorem says that if you have a Lipschitz function from N into R and you take any bigger space, you can extend it always to a function defined in the whole N in a non-preserving way. Okay? So there is no problem of having defined it in a subspace applying this theorem. And now the sum of the norm is close to 2, and I'm done. I have found a function which is far away from this finitely many arbitrary function that I have taken. Okay, this is a proof. The question is, can be this proof adapted to the vector valued case? At first glance, it says that, okay, you have worked with balls, have taken pair of points where somebody has a big increasing quotient. The big point here is Mac-Chain extension theorem. As well as happened with Banach theorems, which doesn't work in complete generality in vector valued cases, Mac-Chain extension theorem is false in higher dimension. It is false even in the case of R2 with the Hilbert norm. That is the reason why we said our classical Lipschitz function spaces will be real valued Lipschitz functions. In the complex case, we will consider it as a vector valued one. So we have a big problem here, and I don't know how to adapt this proof for making it work. So at this point, there are two ways. The first one is saying, okay, I will forget about this problem and I will begin another project. But of course, if you still want to face the vector value case because, okay, it is your thesis topic and you should to give a try to it, you need a different point of view and a different approach to solve the problem. Because here we have an obstacle that we cannot jump in general. Because of that, we needed to search for a different structure of the space Lipschitz. And okay, on Wednesday, you don't want to hear a speech about freedom, okay? We have more than enough until now. But because of the excellent introduction you made about free objects, I will quickly introduce the Lipschitz free spaces, okay? Well, the algebraic definition is indeed quite easy. Consider a metric space N, okay, and a distinguished point, complete, blah, blah. No loss of generality. We define the evaluation mapping in the same fashion as we do in spaces of continuous function, okay? We define delta M acting as F, just evaluate. This is a linear and continuous mapping. And if we consider the closed linear expansion of delta M inside the dual of Lipschitz, it turns out that this the dual of this space is isometrically isomorphic to the space Lipschitz. This f of M is known as the Lipschitz free space over M. And well, the study of this structure is a known word in the study of isomorphic or isometric properties of Banach spaces and connection with many other areas of mathematics. It is a very important space. Well, our interest in this talk will be that it will help us to see this new structure for our Lipschitz. Let's explain. Given a metric space, a Banach space, a Lipschitz mapping from M to X which vanish at the distinguished point, which one? Doesn't matter. The distinguished point is irrelevant. Okay, in this condition, there is a bounded operator hat F, which is defined in the following way. Just simply send an evaluation mapping just to the evaluation, the natural evaluation, okay? The point is that the operator norm of this hat F is exactly equal to the Lipschitz norm of F and makes the following diagram commutative. The commutativity of this diagram is nothing but this equation, okay? Well, this hat allows us to establish a non-linear isometry between Lipschitz and a space of bounded operators from f of M to X, just sending F into hat F. And now we have a new structure on Lipschitz. Okay, there is a big point here. You can say, okay, you have jumped from a Lip structure into a structure of spaces of operators. I don't know if it is simpler or not, but it is another point of view. But you have paid the price of terribly increasing the complexity of your domain. Okay, because of this reason, and because there was an open question in this framework, we consider the case of dual Banach spaces target. In that case, if we consider the space of operator from f of M into X star, this is isometrically isomorphic to the space of operator from X into the dual of f of M. This onto isometry is just the action of taking a joint, and the inverse is taking a joint and restrict. What happened with this space? This is the space of bounded operator from X into our Lipschitz. Okay. Now we have it seems we are done. Now it is a matter of knowing whether this new structure helps us for solving the problem. Well, if life was easy, octahedrality of Y would imply octahedrality of spaces of operator, and we would be done. The point is that life is real, and the following theorem holds. It is known that if you have a octahedral operator space, and if the domain is uniformly convex, then X has to be finally representable in Y. I will not remember the definition of uniform convexity. Maria Angeles did yesterday, but we are not really using it. I will remember that finite representability means that every finite dimensional subspace of X can be represented epsilon isometric as a subspace of Y. So somehow this condition means that Y contains the finite dimensional structure of X. In particular, the implication Y octahedral implies a space of operators octahedral is false. Here you have an example from classical theory of finite representability. This implication is false, and here you have a counterexample. Okay. And the question is now, why am I punishing you with this operator structure? Well, it is true that finite representability is a more or less a strong condition, but it is not anecdotic, okay? It turns out that under certain additional conditions, a kind of reverse can be also obtained. Indeed, a converse can be obtained if we assume metric approximation property, okay? And consequently, if X is finitely representable in little L1, which is the minimal octahedral space, let's say, and if Y is octahedral, under MAP assumption, our space of bounded operator is octahedral, okay? Well, let's give a sketch of proof to see more or less which is the idea. Okay, we want to prove octahedrality. We want to prove this condition. I don't know if pointer says or not. I cannot see. Okay, we are using the condition in Blackboard. So what we want to find is that given finitely many norm-one operator, we want to find a faraway operator. P. Okay. By the very definition of operator norm, this is equivalent to finding an evaluation where the sum has norm bigger than 2 minus epsilon. Okay, but here we can apply triangle inequality, and we get this restriction because all the guys in the slide are normal. So we don't need to condition on T. We need that T is big in norm, where Ti is big in norm, and also we don't only need to send xi to big norm vector, but also we need to send it to an orthogonal part to the vector Ti of xi inside Y, okay? In order to get this orthogonality, we will use octahedrality assumption. And in order to find an operator which is big on all the Ti's, we will use MAP and finite representability. Let's go. Start with operator where Ti are big. Now, since X has a metric approximation property, I can find a norm-one and finite rank operator so that the norm of P of xi is close to 1. Actually, I can find that P of xi is close to xi, but it doesn't matter now. Okay, now I have finite representability, so I can take an epsilon isometry for certain epsilon from P of X into a finite dimensional L1K space. Okay. So we have obtained an operator from X into L1K, which is big on all the x's. Our aim now is to send the image of this operator into an orthogonal part of these vectors, okay? For this, we will use octahedrality. Well, from general theory of octahedrality, but very easy theory, okay? It is done with an inductive argument. The following can be proved. if we take the linear expansion of these operators and given any delta, I can find, because of octahedrality, a whole subspace being delta isometric to an L1 space, an L1K space, and so that this is a L1 orthogonal to our subspace set, okay? This is that every subspace in Y has a finite dimensional subspace Y, which is in Y, which is 1 minus delta orthogonal to set in the sense of the L1 sum. Okay, that is, this satisfies this condition. Okay. Okay. Take one such delta isometry and the inclusion operator. And now the operator we need is the following. We move from X into P of X, then to L1N, L1K, sorry. Then move into S, and then the inclusion operator. I get a norm1 operator from X to Y. Since these are either isometries or delta isometries, and since P of Sy was close to 1 in norm, this operator T sends Xi into big one, almost norm1 operator vector. And also, since the image is included in S, I obtain that the image of Xi goes to this part S, and this condition gives the second condition. I have sent Xi into an orthogonal part to the vectors and unknown. Plus tough play with epsilon and delta that we are not reproducing here. Anyway, as an easy corollary, we obtain that, okay, if we apply that to Lipschitz, if X is finitely representable in little n1 has the metric approximation property, if Lipschitz is octahedral, our space of operator is octahedral immediately. However, Lipschitz function spaces are a very special space. And it turns out that in this context, I can remove any condition on the metric on the Banach space X, and we can prove in complete generality that if M is complete and X is any non-zero Banach space, if Lipschitz is octahedral, then the space of operator is octahedral. And the point is that Lipschitz is octahedral in a very special way. Which way? The speciality of octahedrality of Lipschitz is encoded in this lemma, which reads as follows. Given finitely many functions, I can find a whole subspace of Lipschitz satisfying that the norm of every fi plus every norm1 function in the sphere of Y is bigger than 2 minus epsilon. From here, no surprise. We have seen before that general theory of, well, you have trust me, that general theory of octahedrality allows you to do that when Y is a kind of L1 subspace. The special way in which this space is octahedral is that Y can be taken isometric to CC. And that is the big point here, okay? Well, I will give a quick sketch of this will be just the idea of the proof, okay? Okay, given epsilon, I take the set of epsilon points of fi, okay, for every I. I'm doing this, but I'm taking sequences of epsilon points, okay? And one, I will call this x11, x12, x13, x31. Here the same. x22, x23, here the same. Okay, and I have here the scheme with it. We can assume, since all the VIs are infinite, I can assume that all the points I'm taking are different each other, okay? And now with an inductive argument, I'm going to reproduce this scheme in each level. This will be for constructing G1. Now, in the sequence of second element in the sequence, I'm taking G2 with the same scheme, okay? Take balls, separating them. Inside this ball, take the smaller ball and points where I approximate the norm of Fi, etc. And I define, in general, a sequence of Lipschitz functions satisfying that. Okay, that I find, in other words, a sequence of faraway functions to Fi. Okay. The point is that if you take care with an inductive argument, you can define Gn to have pairwise disjoint support. And now there is a result of Cadets, Martin, and Solovyova, which says that if you have a pairwise disjoint support sequence of Lipschitz functions in a length metric space, your sequence is isometric to C0. This gives 0.2, and 0.1 is computation. Okay. But in any case, what you have to keep in mind is that Lip0 is an octahedral through C0 copies. Okay. And now let's go for this theorem. As before, take finitely many operators, and you want to find a faraway operator from all of them. Okay, you begin taking elements where Ti approximates this operator norm. Now, instead of finding a wild subspace orthogonal to the vector xi, apply the previous lemma and find a subspace isometric to C0, which is kind of L1 orthogonal to the vectors Ti of xi. Okay. Now, what do we know? What do we need? We need to construct an operator from X into Lip0, which is big in norm at Xi, and so that T of Xi belongs to Y, which was orthogonal part to Ti of Xi. Okay, and this is motivated by, this is the same equation I wrote for the other proof. How do we do that? We want to construct that. If you remember the first step, we wanted to send Xi into L1K with big norm. Okay. Now, since our orthogonal is isometric to C0, we will need somehow sending Xi's into C0. So we will need, instead of finite representability in little L1, we will need finite representability in C0. But this is general. Every Banach space is finitely representable in C0. And then I can take the closed linear expansion of the vectors and take a 1 plus delta, 1 plus epsilon isometry from Z into C0. This is given by finite representability, and this is general observability, okay? Which is now the problem. Again, an extension problem. The problem now is that I have phi from Z into C0, which sends Xi into big norm vectors, but it is not defining the whole X. Again, can you extend it in a non-preserving way, kind of vector valued version of Banach theorem? In general, you cannot extend every operator. That is, a vector valued version of Banach theorem is false. However, we don't want to extend a random operator. We want to extend a finite rank one. And here, we call Linde-Strauss, which tells us that given a Banach space X, the dual is isometrically isomorphic to an L1 space if and only if X is a good extension of compact operators. In other words, 2 means that whenever you have a compact operator, for every epsilon and for every subspace, you can extend in a compact way. The resulting operator is also compact. to an operator from y to x, and you increase the norm, but no more than a multiplicative factor 1 plus epsilon. So in essence, we can extend fit. We extend it thanks to Lindenstrauss, because we are taking values in the one previous CC. Okay. Now, since y was isometric to C0, take one isometry and the inclusion operator. And now, this is the composition we need. The norm is close to 1, okay, but as small as we want. T of x is included in the orthogonal part to the vector Ti of xi. This is fine. And finally, since phi sent xi into vector of norm close to 1, and these mappings are isometries, the norm of T of xi is close to 1, and we are done. So, as a consequence, given a complete metric space, and the following are equivalent. Lipschitz is octahedral, M is length, that is the distance is the infimum of length rectifiable curvature in them, and to the fact that Lipschitz of M x star is octahedral for every x. Well, I will finish quite soon, just leaving an open question. Well, from here, there is a clear open question, which is whether you can remove from here the start. I don't know, but it is true that we didn't take care of that. It is probably easy, and we don't know. But okay, it is a natural question here. But my question is related to another property. If you remember at the beginning of the talk, I told I'm going to justify the presence of cadets and Werner, and there was here another point which said Lip0 has the Dogabet property, which means that every rank 1 operator. Okay, I will write 0 here. Rank 1 satisfies that the norm of T plus the identity is equal to 1 plus the norm of T. The question now is, if M is a length metric space, or if Lip0 has a Dogabet property, does this imply that Lip0 MX has a Dogabet property for every x? Well, as far as I know, the question is open. In my opinion, it is not trivial. I obtained recent progresses in the positive direction, showing that the answer is yes if M is an injective Banach space or a Hilbert space. You mean X? I mean M. M as a metric space, if it is, yes. If it is a Banach space which is either injective or a Hilbert space, the answer is yes. Surprisingly, there is an extension problem here. The key point of this result is that M acts as a good extensor of Lipschitz function from subsets of M into M. Okay. As you can see, all the times I face the problem, I have problems with an extension operator or Lipschitz function. We have found here Lindenstrauss theorem, the failure of Maxine extension theorem. Here, what is called in Benjamin Lindenstrauss' book, the construction extension property. So somehow there is here some problem of extending Lipschitz functions or operators, and when you have that, you have problems. But this will be a task for another day or for another mini course. That is all I wanted to tell you. I put here a list of references, and I thank you again for your attention and your attendance.